welcome to this course. If you recall, in the last class we discussed about the free radical polymerization and the step growth polymerations, where we saw that in the polymerization we really do not have that much control. So, today we will continue and we will discuss some of the controlled polymerations, mainly free controlled radical polymerations and anionic polymerations, where the controlling is much better and you can get the well defined polymer following this polymerization protocol. So, the here in the last class, you remember that we discussed the free radical polymerations. Now, we will be discussing in this class mainly the controlled leaving radical polymerization and the anionic polymerization, which are actually used for the polyolefin synthesis mainly in industry and definitely in the lab. So, concept I will cover here mainly the controlled radical polymerations, this one, okay, what kind of initiator you have to use, what kind of condition you have to follow, and the key points for this lecture is, as I told, the controlled polymerations, radical, anionic and the leaving. As you know, the leaving polymerization is always advantageous. In the last class I show the graph that where you can basically have a control over the molecular weight and the conversion of the monomer, and the relation is linear, that a particular time, okay, you will see that the relation within the molecular weight and the conversion of the monomer is linear. So, the molecular weight depends on the monomer concentration, depends on the time. So, this is very advantageous because this is the polymerization is very much controlled. So, that we will try to discuss what are the polymerization protocol in this class. Okay. These are very advanced ways, that is the controlled leaving radical polymerization. Okay. One is the, I will discuss one by one in a very brief way: nitroxide mediated polymerization, atom transfer radical polymerization and reversible addition fragmentation chain transfer polymerations. Okay. And why these are needed, that is the big question. Okay. Why the routine radical polymerations was not sufficient, or what are the advantage? If you recall the last class, we discussed that in all the radical polymerations we need to create a species, the reactive species. Okay. In many cases we use the AIBN or benzoyl peroxide type of initiators, which can be which can undergo the homolytic cleavage at moderate temperature, and then that highly reactive radicals can react with the monomer and you will get the monomer with reactive end, and then can react with another monomer to get the polymerization, and that is the way the propagation happens. Okay. So, but the problem is that in the radical polymerations, if I do these reactions, so you will get the polymer, it is no problem, but you merely have some control in the molecular weight and the linearity of the polymers. That means, you will get the branched polymers. I will discuss, I will show you how you will get the branched polymers. So, you will get the branch polymer, okay. You will get the pore control of stereoregularity. So, this stereoregularity obviously it comes when you are using prochylon monomer, as example propylene. So, in this case you do not have a control on the branch and linearity of the polymers. So, in this case, that is why I cannot tell that 100% that you will get the high density polyethylene. Okay, you may have a low density, high density along with the low density polyethylene, because there may be branching with which depends on the polymerization condition. So, here that is why if you do the radical polymerization, it is very difficult to get the high density polyethylene. In most of the cases you get the low density polyethylene. Why it is? Because you know, if you recall the radical polymerization discussed in the last class in quite depth. So, this is your I will just show the polymer with reactive end. So, this is okay. I am just showing the not drawing the entire chemical structure of the polyethylene. I am just showing the active end. Okay. This chain type zigzag drawing the bond means there is a this is a polymer chain. Okay. And that is actually convention we follow during the representing the polymer. So, what I am doing, I am just writing the radical, which is this is the your active end, okay, which further reacts with another monomer. This is the active end with the radical. Now, you will see I have also same here available, okay, in the polymerization where we are doing the polymerization. Now, what may happen here, okay, if I suppose this hydrogen, okay, I am just removing this one, I am just drawing so that it is easy to understand. Now, again the homolytic cleavage may be possible here. So, what happens, this can couple and this. So, what will happen now? So, this is giving your dead end, okay, CH3. So, this is dead polymer, but now you what happens, you are getting here like that. Okay. So, now your see the here you please understand what happened here. So, here your radical is at the end of the polymer, that means the active center at the end of the polyethylene, and here the active center in the middle of the polyethylene chain. So, this is the mechanism where you get your branched polymer, because this one now can react with your monomer and you will get basically branched polyethylene. Okay. So, that is the reason why you get the branched polyethylene if you follow the radical polymerization. Okay. And obviously, other problems associated with that, you will get a broad distribution of the molecular weight, because there is several ways of termination, as we discussed in the last class, that simply coupling with this one and this one, okay, or there is other possibilities that this can also couple, this can also undergoes another mechanism of termination, that is the disproportionations that we discussed in the last class for the polystyrene, but similar situation may happen for polyethylene as well. Okay. So, here is my this one and here is my other chain. Now, what may happen here, you will see that this is then homolytic cleavage of this one. Okay. So, this is one, this forms the double bond and this comes out. So, this one then forms the H dot. So, this one now can react with this one. So, you will get eventually that two dead polymers, one is with this end and one with the vinyl group, okay, this end. So, this is this kind of termination is called the disproportionation, and another way it is very easy to understand, this may couple with another one. So, you will get the double molecular weight, okay, due to the just simply coupling of this reactive polymeric end. So, there you see that there is a possibilities of different unwanted reactions, and who is the responsible for that one? Because the reactive, highly reactive nature of the polymer end is the you can say is a culprit. Okay. So, that is why it is very difficult to control this polymerization by the free radical polymer, and that is why you call the free radical polymerization. So, that is why you will see the polydispersity, if you use the PDI is quite high here, even sometimes you may get very high molecular PDI value 2 to 10 something like that. But you have to understand that do not think that PDI 1 or 1.5 or 1.2 is always kind of advantageous. So, that again it depends on the what application you want to do it. Okay. So, sometimes purposively we make the polymer with high PDI. Okay. So, the students or the learner who are from the industrial background, I am sure you are very quite familiar on this one. Okay. Fine. So, the main take home message from this free radical polymerization, that we do not have much control, we get a poor stereolect selectivity, chain length control is very poor, we get very branched polymer, and that is why we cannot really follow this polymerization protocol, where the more fining architecture is needed for the different polymers. As examples, you see that this is the linear polymers. Okay. This is sometimes we need the this is called LLDP, we discussed already. We need sometimes like star like polymers. Okay. We need the grafted polymers, okay, like this one, where all the side arms should be equal space. Okay. And these as I discussed, this is the beauty of the polymer, the same polymer composition, but if you change the architecture, you will get quite different properties. Okay. And obviously, we can apply for different applications. Okay. So, in the so this is the problem, that the very poor control of the free radical polymerization, and as I told that the main culprit is the reactive species, okay, associated with the free radical polymerization. Now, in this polymerization, you see nitroxide mediated polymerization, atom transfer radical polymerization, reversible addition, fragmentation, chain transfer polymerizations, all were developed quite recently, okay, compared to the other traditional radical polymerizations. Those are all discussed, all are discovered after 1990 to 2020, after 1990. So, you understand is quite recent. Okay. So, let us discuss that what are these and what are the basic concept to make this radical polymerization to control and living. I will not go in depth about the kinetics, I will just try to showcase that what are the basic strategy we have followed to make the this radical polymerization more controlled. Okay. So, in the free radical polymerization, I will just give another pictorial diagram here. In the free radical polymerization, what happens here? You have the radicals, the monomers, okay, like that one, okay, and you make the initiator molecules. Okay. So, you make reactive by putting the initiator, okay, and so these are now the you can tell the reactive with initiator. So, I am just putting like this one, Okay. So, these are now reactive monomer, you can say. Now, you have lot of monomer in your polymerization container. Now, what will be happen as it is quite reactive. So, what will happen, you will get the polymers with uncontrolled chain length. Okay. So, ultimately what you will get? You will get the polymers with quite broad molecular distribution, but because this is highly reactive. Now, if we can control this polymerization, then what will happen? So, here again I have monomer, and here I am putting initiator, and again I will get like this one, but if I can control it, that if I can reduce the reactivity of this active species, what we can get? We can get the almost similar chain length of the polymers. Okay. Now, how I will do it? So, basically we can you will use the concept of the dormant species. Dormant species means what we will do? We will try to make equilibrium about the highly active species within a dormant species. So, we will apply the concept of the dormant species here, to make the highly active radical to make less reactive, or whenever it is needed, it will again react with the monomer, but it will be in a controlled way. Let us discuss what is this. So, this is the initiator. In the free radical, you saw that initiator we are using AIBN or the peroxo type of radicals. Here we will use the different type of radicals. So, actually this is prepared very easily by from here. This is and so you will see that it's called the this species called tempo, that is a piperidine derivative. You see 2,2,6,6 tetramethyl piperidine 1 oxyl, and this is called the styro tempo. So, if you just heat it, you can get this tempo radical. So, this is again initiate by a radical, but the nature of the radical is different from the radicals you are getting from the AIBN or the tempo. So, what we are doing here? So, let us. So, this is my initiator, that is this one is the initiator, although there are various initiators are available at this moment, but this is the commonly used, very common initiator we used even in industry and also in the lab, but there are several initiators are available. So, what happens here? You get the two radicals, one is the R dot and one is the Z dot. This is the reactive radical, and this is the stable radical. Now, what will happen? this one. So, this is the stable radical, this one. So, this is the Z. Okay. Now, in the next case what happens? So, your R dot reacts with monomer. So, here the monomer may be polyethylene, or sorry, the monomer may be ethylene or any other vinyl containing. So, anything like, let us say the monomer I am writing here, okay, like in the common. So, let us say this is my monomer. Okay. So, this may be olefinic, may be acrylic type of monomer, anything. So, now this one will react with monomer and you will get the okay. This is, so this is basically reacting with monomer and eventually you will get. So, if you have a lot of monomer, so you will get the polymer with active end. So, this is, we can tell it say is a propagating radical. Okay. So, the active end at the polymer end. Now, I have Z available, that is the stable radical. So, this can reacts with Z dot and you will get the okay, the R. So, M N now Z. Okay. So, this is basically dormant. Radical. So, is there is a equilibrium with this one. So, I actually if I follow this one, we should write as a equilibrium sign here. So, this equilibrium exists between the this R M N dot and Z dots, and it forms the R M N Z. So, this is the dormant radical. Is basically what we are doing. We are controlling the reactivity of these very active species, and that is the strategy we are following for nitroxide mediated radical polymerization. Okay. So, here and this is by this way what we are doing, we are basically suppressing the bimolecular termination. Suppressing the bimolecular termination, which is, if you recall, which is another one of the biggest problem if we follow the free radical polymerations. Okay. But the disadvantage is that this polymerization is quite slow. Okay, in NMP you will get a fantastic control over the molecular weight distribution. The PDI is very nice. Okay. The PDI you may get almost like 1.2 to 1.8 for some of the polymers. Okay. Good control on molecular weight and PDI. Okay. But the disadvantage is that it is quite slow polymerization. Okay. And sometimes it take 2 to 3 days like that, but the polymerization you will get a very good control over the polymerization protocol in this polymerization protocol. So, this is a one very popular method, very recent method, advanced method, that is a nitroxide mediated polymerization, and it solved the uncontrolled polymerations in free radical polymerations. Okay. So, there is another method is called atom transfer radical polymerations. Here you will see that again that you have to suppress the bimolecular termination by again the concept of the dormant species. So, where what we use, okay, you have to, I will give one example what kind of initiator you will use. So, this is like this one, okay. This is tertiobutyl group, and many wide varieties of vinylic containing monomers you can use. One of the monomers is methyl methacrylate or the sorry okay. So, this is one of the, I just want to give one real example of the monomer what we can use, okay. Yeah, acrylic type of monomer you can use, and here we will be using one catalyst, okay, and this is the metal catalyst, okay. We will use, here you will see we will use the like a copper 1 complex by, so you have to choose one, mostly we use transition metals complexes where there it can undergoes one electron oxidation and form the copper 2, okay. So, that and similarly you can use other complexes like ruthenium 2 or iron 2 like that, which can undergoes the oxidation like this one, okay. And I will tell you, okay, in very shortly why you need it, because there is a step where that catalyst would undergo the one electron oxidation to facilitate the polymerization. So, you will understand why it is needed. Okay. So, now I need a catalyst. One real example is copper bromide, okay. And what you will get? You will get the polymer of this one. So, this is your end, that is this end, okay. So, this one and this methyl, and you will get your yes, okay, and here OMe, okay, and here you will see that this bromide, so will be here, okay, and also here one ligand is used to facilitate or stabilize to form this copper 2 complex. So, one tridentate ligands commonly used is this one, okay, and here like that. So, this ligand, the ligand you can use anything, we generally use anything means any chelating type, good ligand, chelating type ligand you can use to facilitate the formation, to stabilize the formation of the copper 2. Okay. Now, you will see here what we are doing. So, we are now the bromo is at the end. Now, if when it will react with when it will react with copper bromide again. So, what will happen? It will form the polymer. So, I am not writing this one, I am just straightly getting this polymer, okay, and you will get the copper bromide 2. So, what we are doing here now again, this is your active species with radical. So, I can just write as a P n dot. Okay. So, now you will see what happened. So, again this is a you can say dormant species. Now, we can again reinitiate by using properly judiciously chosen catalyst transition metal complex here to reactivate again to form the radical, and then it can again react with the monomer. This can again react with monomer to get the polymer. Okay. So, you will see that again this is a concept of this dormant species. Okay. So, very similar concept as the nitroxide mediated polymerization. So, here again is basically I am suppressing the bimolecular termination. Okay. And PDI is quite good. Okay. Here again, okay, you can get almost 1.1 PDI. Okay. And the problem, but only problem is that the polymerization is happens quite elevated temperature. Okay. That is the one of the problem. So, it is need around like some cases you need 120 degree centigrade temperature. Okay. But another disadvantage that if you want to use these polymers, okay, for any biomedical applications or any material science application, you have to be very careful about the contamination of the transition metal complex impurities. So, you have to really be very careful to purify the polymers. Okay. So, that was the advantage disadvantage, but you see that we can have a very good control over the normal free radical polymerations using the concept of atom transfer radical polymerization. Okay. So, this is the next one is another way of controlling the radical polymerization, that is the reversible addition fragmentation chain transfer polymerization. So, here what we use? We use a initiators, okay, like AIBN again, okay, and we use a very special reagent here. This is called Raft reagent, that is a dithioester derivative, dithioester derivative. Okay, that is basically the S. Okay, this is like that. Okay. So, this is the dithioester moiety. Okay. So, now what happens again, we are using the concept of the dormant species here, and a wide variety of the polymers, as example monomer, as example any acrylate monomer, you can do the polymerization using this raft, and this is also again very effective polymerization protocol to make the polymerization in controlled way. So, this is my initiation, okay, initiation step, and here you will see this is the reversible chain transfer. Okay. So, this is basically your propagation step. Now, how does it happen? So, this reacts, okay, this PN is reacts with this radical is reacts here, okay, and from this is okay. Yeah. So, you see that this is my initiation step. You got a polymer with reactive end by attacking that radical initiator. Now this one react on this one and you get the that radical here. So, this is here is now your radical. Okay. Now, there is a again rearrangement. So, here and this is here. So, this is the formation of the that radical again, and you will see that your polymer end is now embedded on the this dithioester moiety. Okay. And you will getting the now again this R dot you will react with monomer again and you will get the PM dot. This PM dot okay, again will react. So, this is basically your initiation step. Okay. So, this is your you can tell reinitiation step because this one is your first initiation and there this is the polymer embedded on the your dithio unit. So, this is also again can reinitiate by this R dot. So, you will get the PM dot. Now, this PM dot can react with your that polymer where the end group is the dithio moiety, and then you will get the your again this PN dot polymer. This initially it was a PM dot, now it is a PN dot and PM is again embedded on the dithio moiety. So, this is basically chain equilibration step you can tell. Equilibration step you can tell. Okay. And at the last is termination. Okay. So, all this I dot, R dot, PN dot and PM dot will get the undergo the termination by radical quenching. Okay. So, again here this is also very nice method for to get the well defined polymers by using the concept of the reversible addition fragmentation chain transfer polymerization. And here the specialty that you have to use this kind of dithioester moiety, this is called the raft agent. Here again you can control the steps okay, by appropriately choosing the R group and Z group. I will not go in a depth discussion on this one, I just I wanted to give the concept. So, what is the common factor here okay, in this radical polymerization, the control radical polymerization? In all the case you will see that in NMP what we did, we put a we use the concept of the dormant species. Okay. Here in this case if you in this case this was the dormant species in NMP. Okay. In ATRP again this is the dormant species if you recall, okay, because this again reacts with my let us say copper bromide to make the radical again. And in the raft process, which one is the dormant species? We are getting the dormant, if you recall, okay, you getting the S, that is the dithio moiety like this one. Okay. So, you will see that this again the dormant. So, we are using the concept of the dormant species to control the highly reactive nature of the radical. So, here you will see that thermal dissociation of the dormant again react or reinitiate the polymerization. Okay. Here we are activating the dormant species activating by transition metal complex catalyst. Okay. As example like copper bromide or any other iron 2 or ruthenium 2 complexes. Okay. And here we are doing the degenerative transfer, okay, of the dormant species to make it again active. Okay. So, this you see a what I called a very intelligent way, intelligent strategy to make, in all the cases, to make the controlled nature of the radical polymerization, to make the uncontrolled radical nature of the polymerization, to make it controlled and well defined. Okay. So, in here you will see that we have, in the conclusion, we have, you see this, we discussed the how we make the radical polymerization uncontrolled to controlled by following the strategy of the dormant species to make equilibrium between the dormant species and the active species in the radical polymerization. And you understood that how this radical, the controlled radical polymerization, this is called CRP, allowed us to make the well defined polymer controlling chain length and obviously the architecture. Okay. So, whatever the content I have discussed here, you can find in a well very popular textbook like George Orion, Lovell and Young, and the Charles Carroll. So, all are available, easily available. And next class I will discuss very shortly about the anionic polymerization, and this is also another method of making the living polymerization, and then we will enter to the polymerization, very special polymerization protocol, that is the coordination catalytic polymerization, where you will be using the transition metals to make controlled polymers, and where you will see that we can control the molecular weight and also the architecture of the polymers and also the stereoregularity of the polymers, which is very interesting, and we will use the concept of the unique organometallic reactions in this coordination catalytic polymerization. So, that must be very interesting in while we will discussing about the organometallic complexes catalyzed polymerization in the next class or so. Thank you very much.